Hello everyone. Now we will continue our learning on reservoir simulation. And in this video, we will talk about PVT simulation, PVT analysis, and we will do that in CMG Winprop software. All right, so Winprop, Winprop is a very popular software to perform PVT analysis and simulation. There are actually numerous software to do that, but WinProp is, I think, one of the best. Okay, so we will now perform simulation, PVT simulation using WinProp. It is from CMG. So we are now inside the CMG, and you can see in CMG, we have builder, all right, and then simulator like IMAX, GEM, and STARS, and to perform history matching like using CMOS, and to perform PVT simulation, PVT analysis, we will do in WinProp. Okay, so now let's go ahead. I will double click the WinProp and we will enter this software, this WinProp, maximize. Okay, so this is the first window. You can see we have file, we have characterization, and you can see we will have options for plus fraction splitting, component lumping, regression, and some calculations. You can see single phase fluid, two phase flash, all right, and then saturation pressure, saturation temperature. If you want to create two phase envelope, some of these features we will use in this video. And then laboratory, okay, laboratory analysis like the spirator, the swelling test, spirator saturation pressure, differential libration, constant volume depletion, CVD, right? And CCE, constant composition expansion. We can do that in WinProp. Simulator PVT, if you want to generate the PVT to be used in the simulator, like for GEM and black oil PVT, for IMAX, and for STARS. Preference, if you want to create the text editor either in Notepad, TextPad, or in Word or CMG editor. And help, as usual, if you open the contents, it will direct you to the internet. So I'm going to close instead. Okay, so that's for the header. And you see the model tree here. This will be used in all of our steps. And here you can see the title, EOS or equation of state, and the units. For the header value, command line, for example, in this video, I'm going to create gas condensate. So I'm going to make a title, command line, gas condensate, and also gas condensate. Title line, maybe the field, or maybe the well from which the fluid is taken. You can put anything here in title line 1, 2, and 3. And then the basis that will be used throughout the entire simulation, equation of state, the default is Peng-Robinson 1978, or can also 1976, SRK, Swaffer-Reddick-Wong. The unit can be PSIA and degree Fahrenheit, which means field unit, or KPA and Celsius, which means SI, international system, or maybe this one for laboratory unit. I prefer using field unit, so we are working with PSIA and degrees Fahrenheit. And the fit can be in mole or mass. I think mole is more preferable in many PVT analysis, right? So we will select mole in this tutorial. Okay, so far so good. Now in the model tree, you see we are still in title EOS units. Now we go to the next section, component selection properties. Okay, here we will select our component. Either it is components that are available in the library, or maybe hypothetical component that we will create by our own data. Okay. Of course, as usual, we go to basic. We will use this one. Insert the components that are available in the library. Okay. And this is the library components name. You can see H2S, CO2, some basic components, right? And then nitrogen, CH4, methane, ethane, propane, isobutane, normal butane, right? I have my own data. I have my own composition. I have my own components. And then, so I will just select and present it to you. Okay. So in this simulation, we will involve carbon dioxide, and then I will press shift. I will select also nitrogen, CH4, methane, ethane, C3 propane, isobutane, normal butane, and then isopentane, C5, and then normal pentane, and also hexane. Okay. After selecting that, press this one. So from the from the library components, go to selected components, click OK, right? So these are the selected components, and you can see this one, and then the critical pressure, critical temperature, eccentric factor, molecular weight, volume shift. If you double click, you can set to 0 as per default, or you can also set to interface correlation value, use internal ZRA correlation. If you are not familiar with it, I recommend you to start simple. So we will use default numbers. Okay. And then this one, volume shift, Z factor. Okay. And then this one, viscosity, omega A, omega B, beta factor, specific gravity. I think it's boiling temperature. Okay. And others. Again, if you want to be familiar with it, I recommend you to open the manual, going to help. Okay, so far so good. So these are the basic components that will be involved in our simulation. Okay, basic components in our fluid. Okay, now I actually also have C7 plus component. Okay, the heavier component, C7 plus. And of course, it's not in the normal library. So I will construct, I will create a new component, my own component, which I call C7 plus. Okay, to do that, go to this one, insert on component. Okay, let's read the note, or maybe the header first. This is the custom hydrocarbon component definition. It's customized. So it's based on our data, our description, our preference. Okay, and let's read the note. First, component name, maximal 8 characters to be entered, and I will call it C7 plus. It's not CR7, Cristiano Ronaldo. No, it's C7 plus. All right, for the second one, for better property estimation, please enter all of the following four properties. So if you have performed the laboratory data to analyze this component, you can provide to the Winprop either PC, TC, eccentric factor, and molecular weight. But you know, critical pressure, critical temperature, and of course the eccentric factor, usually we don't measure that. These two are simpler. So, or at least two of the following three properties. Molecular weight, it's easy to measure. Specific gravity, of course, it is even easier to measure. And then the normal boiling point in degrees Celsius. And I will provide that in this case. And let's say from my laboratory, I know that the molecular weight of my component is 185, okay? Or 184 instead. And the specific gravity, okay, the weight or the density of this component divided by the density of water is 0.816, okay? And then we need to select the correlation that will be used for physical properties correlation. We will follow the basic, or we will follow the default. It's 2 correlation. Critical properties also 2 correlation. Eccentric factor correlation, we don't have any other option, so we must select Lee Kessler, or another one is Admister. I prefer Lee Kessler. Okay, and the rest will be calculated instead by the Winprop. Okay, so if you click OK, this one, okay, you will have this own component here, C71, and the critical pressure, critical temperature now is calculated. Eccentric factor, this one is our data, molecular weight. This one, volume shift, Z factor, and the other one will be calculated automatically by the CMG Winprop. Okay, so far so good. All right, and this is the component. Okay, and then this one aqueous phase model option. We can use the default, including the viscosity model type. We will follow first the default. Here we use Joshi Steele Thodos correlation with all these parameters. All right. So now Winprop asks, the component data has been modified. Do you want to apply the change? Yes. The number and or order of the components has been changed. Please verify the compositions. Okay. Let me check. Oh, I think we have a problem here. We need to insert again our library component. So yeah, I will insert this one. Okay, click OK. All right. All right. So here we have the library components and also our own component, the C7 plus. Apply change. Okay, so in total we have 11 components. All right. Okay. If you want to give comments here, you can input your comment, and make sure you also input this one, default reservoir temperature in Fahrenheit. Let's say the reservoir temperature is 285 degrees Fahrenheit. Okay, and again in comments, I will input gas condensate. Okay, so far so good. The components and then number of components. Yeah, if you want to move the C7 plus to make it, yeah, looks better, you can use this one. I will put C7 plus to the bottom. All right, and apply change. Okay, so in component, you can check the component property plot. Here we have critical pressure against the molecular weight. And then this is the critical temperature plotted against the molecular weight, and eccentric factor, thermodynamic properties plotted against the molecular weight. Okay, and then logically we will input the composition, and that's what we will do. So to composition, later we can also look the component composition plot, but here we will provide the composition. Comments, composition, you can also leave it blank. And the comment is enter the composition in mole fraction or percent. Normally, primary corresponds to the reservoir fluid, okay, primary, whereas this secondary column corresponds to the injection fluid, if applicable. If we have injection fluid, blanks will be replaced by zeros, okay? And if you want to normalize, you can click this button, but I will provide my components or compositions first. Let's say the CO2 237. This is the mole fraction or mole percent instead. Nitrogen 0.31, CH4 7319. This one 7.8. C3H8 is the propane 354, 3.54. And then isobutane 0.72. N means normal. Normal butane is 1.44, whereas the isopentane is 0.65. And you can see the real-time summation. Normal pentane, NC5, 0.869, whereas this one, hexane, is 1.08, and the rest is C7 plus, which is 8.21. And if you sum all of these compositions, it will be added up to 100%. So no need to normalize composition. Okay. And then if you go to component composition plot, you will have this one. Okay. It's easy. It's just a bar chart showing you the components and also the composition. We have carbon dioxide, nitrogen, methane, ethane, propane, isobutane, normal butane, isopentane, normal pentane, hexane, and C7 plus. All right, so far so good. Now we can check at this point, we can check the characterization, but it's still inactive. But if you go to calculations, yeah, it's still also inactive. Why? Because instead of pressing this one, we should press this one. Okay, showing CMG these numbers. So now it's active. The characterization, you can perform these operations, but now we will go to calculations. Okay, we can do several analysis, but let's start with, or let's check, for example, these operations, or if you want to generate again, if you want to generate the PVT to be used in IMAX, black oil PVT data, or to be used in GEM, or to be used in stars. Okay. And let's say the first calculation that we want to run is saturation pressure. Okay, let's open. And now in our model tree, we will have a new folder, saturation pressure. Okay, here, if you want to perform pseudo equilibrium saturation calculation using liquid phase fugacity and beta factor, you need to provide in this table. Okay, the measurements, which means you prefer to run regression. Okay, but let's say we don't know that here. We don't know that in this time being. So we will not do regression. We will start very basic. So we will just calculate instead of matching or instead of regression. Okay, so now for saturation pressure, the temperature 280 and the saturation pressure estimate, let's say it's 1000. And the calculation option, it is bubble point or upper dew point. Okay, because we are handling condensate, so it is dew point instead of bubble point. Okay, so I've provided the Winprop with temperature and also the saturation pressure estimate. Later on, the CMG will run the calculation and give us the result. Okay, so far so good. And another calculation that I want to perform is to perform two-phase flash. Two-phase means two phases. It is liquid and gas. The first phase is gas. The second phase is the liquid. Okay, or in this case, the condensate. Okay, for two-phase, you will find another, or you will get a new folder, and you can input the comments if you want. Now the pressure data. The pressure data, the pressure that will be used as reference is standard condition, which is 14.7 psia or atmospheric pressure. The pressure, the condition that will be used for two-phase flash. And then if you want to generate the range of pressures, we can use pressure step here. It's a 0 and number of pressure steps 1. And then for the temperature 60, standard condition, right? Or stock tank condition. And the rest, we can follow the default condition. And then let's say I want to generate the phase envelope. We can do that also in calculation. By the way, this one, the yellow buttons or yellow features here are actually the same with what we get in characterization. You can see plus fraction splitting, component lumping. You can find also here, like this one, component lumping, this one plus fraction splitting. Here, you can find them in characterization and calculation. You can find them here also. For example, if you want to create two-phase envelope, in calculation, we can find in two-phase envelope here. But in this bar, you can find here two-phase flash, asphaltene, multiple contacts, compositional, this one, two-phase envelope. Select. Okay, we get a new folder, and then envelope type XY phase envelope. Okay, we will start basic, simple, XY phase envelope. Y-axis will show the pressure, whereas the x-axis will show the temperature. We can use default numbers. It will be used as a range in which the envelope will be generated. Okay. And then, for example, starting temperature, I want to start from minus 80 because I'm also interested in what happened in minus degrees, okay, minus 80, for example, and the rest, I will follow the default, including these construction controls, fit, key values, and others. We can follow the default. And also, I want to perform another two-phase flash operation. Okay, here I want to have ranges of pressure starting from 200, 250 psia with step of 250 psi and the number of steps, for example, 25. So it will be 250, 500, 750, 1000, and so on and so forth. And the temperature at reservoir temperature, which is 280 degrees Fahrenheit. Okay, and the rest are as per default. Okay, and then experimental, if you want to perform regression or matching, you can input your measurements here. Also, for the K values, plot control, which plots you want to generate. Let's say I want to generate phase volume fraction, compressibility factor, K values, and viscosity. But basically, we can generate all of these plots. Okay. At this point, we can save this exercise. Okay, you can open the file and save as. All right. We will select save as. For example, this one, I want to call this one gas condensate. Okay, I will save it at my desktop. Click save. Okay, so far so good. And now, after setting up everything, okay, we can run just by clicking this run simulation button. All right, the simulation results will be here in this model 3 view. Event log, this one, okay. Validation, okay. And then the simulation output. These are the comprehensive results that you can learn starting from this header. This is the dimension, file name, the component name, CO2, nitrogen, CH4, and the rest. Critical pressure, critical temperature, all of these results will be visualized in terms of plottings, okay? AC, eccentric factor, molecular weight, volume shift, everything is 0 as per our reference. Okay, critical volume, this viscosity, omega A and omega B. Okay. The composition that we input. And this section is the operation that we run. We do saturation pressure, as you can see here, saturation pressure, and then two-phase flash, and then phase envelope, and then two-phase flash again. So if I go to simulation output again, okay, here the saturation pressure, the two-phase flash, and also two-phase envelope, and then two-phase flash again, and okay, and then this is for better visualization, the component, okay, and then also the properties, the Z vector in liquid and in vapor, molar volume, okay, ideal H, enthalpy, ideal CP, I think it's heat capacities, okay, and then ideal entropy, the entropy, density, viscosity, interfacial tension, all of the fluid parameters you can find here. Okay. And so this one, okay. What is this? This is the two-phase diagram construction. Okay. So if you use all these numbers, you can generate or you can plot your own phase envelope. But of course, it will be quite tedious if we plot it in our spreadsheet. So let's just rely on software to visualize the phase envelope for us. Okay. So basically all the visualizations that we see come from this, I think this script or this code. And you see this one, the phase envelope, but we will have better visualization later. This two-phase diagram construction still. Okay. And this one is multi-phase flash calculation with two-phase equation of state flash, which use QNSS method. If you are interested in knowing all of this, you can open your textbook or open the CMG manual. Still multi-flash flash calculation. Okay. You can exercise the simulation yourself. So from this simulation output, we can go to simulation graphs. Okay. Still in the model view, this one is simulation graph, PT diagram, the phase envelope. Okay. This red point is critical condition, the pressure and the critical temperature. Okay. This dome is two-phase boundary area, and this line is two-phase boundary, two-phase boundary. Okay. Inside this dome, you will have mixtures, gas liquid mixtures. Okay. Whereas here, above this dome, you will have gas phase. Okay. At higher temperature and higher pressure and higher temperature. Whereas inside this dome, below this line, you will have mixtures, condensate as liquid and gas itself as gas phase, which is very important for you to know at which phase your fluid is during the history of your pressure. Okay. In reservoir pressure, maybe you will have gas. In well condition, well pressure, maybe we will have condensate. Okay, condensate liquid dropout. And maybe also in surface pressure condition, you will also have condensate, two-phase conditions, maybe. This PT diagram, this phase envelope will inform you about that. Okay. And phase properties or solvent mole fraction or phase properties, we have 5 pages. The first one is liquid phase volume in percent plotted against pressure. Okay, at 280 degrees. What is page 2? Is vapor phase volume plotted against pressure. Page 3 is the Z factor, the liquid Z factor. Page 4, the vapor Z factor. Page 5, the K values. K values is mole fraction in vapor phase divided by mole fraction in liquid phase. or in mathematical representation, it's yi per xi. Okay, so mole fraction in vapor phase divided by mole fraction in liquid phase. And the color indicates the component. So this one is nitrogen. Okay, you can like this. Right click, you can print plot, you can copy to clipboard if you want to plot it on spreadsheet, for example, or if you want to save file, plot property, if you want to adjust the color, the size, the type. Okay, like for example, the line can be solid, can be dash dot, dash dot, dash dot dot. The size, you can change the color. You can put markers, either circle, square, triangle, cross, and others. And you can click apply after that and OK. Whereas this one is the minimum, maximum, and step size for x-axis, the horizontal axis, and y-axis, vertical axis. Okay, so in nitrogen, okay, K values is quite high, which means mole fractions will tend to be on the gas phase side, okay, the vapor side, because nitrogen, it's gas basically. So the component will tend to prefer the vapor phase, okay? And I think this is the C plus, right? C plus, it's heavy component. So logically, heavy component, the liquid component will prefer to be on the liquid side, which means the K values will be small, okay? Because the component will prefer to go to the liquid phase side. And of course, if you divide the vapor per liquid, liquid is high, means K values will be low. That's why you have this plot like this, the lowest plot, C7. Whereas nitrogen will be at the top because the, the, the nitrogen component will prefer to go to vapor side. Okay, so that's what will we have. Of course, Winprop is not that simple. You can input all many kinds of fluid that you have: condensate, black oil, gas, dry gas, wet gas, heavy oil. Okay, even if you want to perform CCUS analysis, the CO2, you can do that also here. And hopefully in the next opportunity, we can exercise more features in this software. But for now, I think we can call it a day. So in this tutorial, we learn about gas condensate PVT simulation. We input the component that we have. We have 11 components. 10 components are available in the library, the basic component, and one component, we create a hypothetical component. We have our own component, which is C7 plus. To generate this component, we provide with molecular weight and also the specific gravity that we obtain from laboratory measurement, for example. And of course, don't forget, we provide the composition for each component, and we perform several calculations like two-phase flash. We generate the phase envelope, okay, and then the saturation pressure. And of course, after running the simulation, we get the simulation output in terms of script and of course in terms of plots. Okay, so that's all. See you again. Thank you.